It's kind of surprising, isn't it? You see kids learn their basic addition and subtraction facts, and they seem ready for anything.
Mm. Mm.
Then a seemingly simple word problem comes along, and suddenly it's like they're speaking a different language. What's behind that disconnect?
Yeah,
That's exactly what we're going to delve into today.
absolutely. It feels like the most straightforward next step, but for many children, it's a significant hurdle.
Hmm.
And for this deep dive, we're looking at a really comprehensive body of work, a decade of research out of the University of Leuven in Belgium.
Oh, interesting.
They've been meticulously investigating how children tackle these elementary addition and subtraction word problems.
Leuven, Belgium, a fascinating place for this kind of in-depth study. And as I understand it, this research wasn't happening in a vacuum, right? It really built upon some important groundwork laid here in the U.S.,
That's right.
particularly the work of Carpenter and Moser and Greeno and his colleagues.
Exactly. The American research provided a vital foundation. Carpenter and Moser were instrumental in gathering, detailed information about which types of problems children found difficult, the various strategies they employed, and the common errors they made.
Oh.
Then, Greeno and his team took a more theoretical approach, developing computer-based models to try and understand the underlying mental structures and processes involved in solving these problems.
Right, the models.
Yeah. They even gave us that useful classification of word problems into change, combine, and compare types, which they further broke down into 14 different categories based on what the unknown quantity was and the nature of the action or relationship described.
14 types. Wow, that's much more detailed than just thinking about whether to add or subtract.
Mm-hmm.
So with that framework in place from the American research, what were the key questions or areas that the Leuven researchers focused on?
Well, what's particularly insightful about the Leuven research is their deep dive into the semantic structure of these word problems. They uncovered strong evidence that the way a problem is worded, the underlying relationships it describes, has a profound effect on its difficulty for children.
Even when the math is the same.
Even when the required arithmetic operation remains the same. Yeah.
That's the kind of thing that makes you rethink something you thought was simple. Can you give us a clear example of how that semantic structure makes such a difference?
Sure. Consider these 3 types of problems that second-grade students worked on in one of their studies. First, a change 2 problem. Pete had 6 apples. He gave 2 to Anne. How many does he have now?
Okay, straightforward subtraction.
Right. Second, a combine 2 problem. Pete and Anne have 9 marbles altogether. Pete has 3 marbles. How many marbles does Anne have?
Also subtraction, but feels different.
It does. And third, a compare 5 problem. Pete has 8 cookies. Anne has 3 fewer cookies than Pete. How many cookies does Anne have?
Okay, again, subtraction.
All 3 solvable by subtracting, yet the success rates were quite different. 88% for change 2, 62% for combine 2, and only 36% for compare 5.
Wow, 88 down to 46%. That's a huge difference in success rates for problems that all boil down to subtraction.
Huge.
So it's clearly not just about knowing how to subtract. The story the problem tells really, really matters.
Precisely. The Leuven research generally supported the RGH analysis, that's Riley, Greeno, and Heller, in that different semantic structures do indeed lead to different levels of difficulty.
Right.
However, they also found some interesting variations. For instance, in the Leuven studies, a change 3 problem, like Pete had 2 apples and gave him some more, now he has 6. How many did Anne give him? Turned out to be more challenging than a change 6 problem. Pete had some apples, he gave 5 to Anne, now he has 7. How many did he have at the start? Which wasn't always the trend reported in the earlier American findings.
So not a perfect one-to-one match. It sounds like the Leuven data added some nuances to the picture.
Exactly. Nuances is a good word. When the Leuven team looked at the patterns of correct and incorrect answers from individual students and compared them to the patterns that Riley, Greeno, and Heller's computer models predicted, well, they found less empirical support for those specific models than what the original authors had reported in their own studies.
Okay, so if the existing computer models weren't fully explaining what was happening, where did the Leuven researchers turn their attention to really understand why children were struggling with these problems?
This is where it gets really fascinating. The Leuven team shifted their focus to understanding the representations that children were forming of these problems in their own minds.
Representations, okay.
They didn't just look at whether the answer was right or wrong. They used a really comprehensive set of methods to try and get a window into the children's thinking. They asked them to solve the problem, but also to retell the story in their own words.
Okay.
Explain how they arrived at their answer, build a physical model of the problem using objects, and even write a number sentence that matched the situation described.
That sounds like a much more in-depth way to understand what's going on than just grading their answers. So what were the key insights they gained about where these difficulties were actually originating?
The crucial finding was that many errors arose because children were forming inappropriate mental representations of the problem.
Ah,
And this often wasn't simply a matter of not knowing whether to add or subtract. Instead, it frequently stemmed from fundamental gaps or misunderstandings in their conceptual knowledge of the situations being described.
okay, so deeper than just checking the operation.
Much deeper. This really challenged the earlier notion that the primary difficulty was just selecting the correct arithmetic operation.
That makes perfect sense. If you don't truly grasp the situation that the problem is describing, how can you possibly know which mathematical operation to apply? Can you give us a specific example of one of these representational errors in action?
Absolutely. Let's revisit that combine 2 problem. Pete and Anne have 9 marbles altogether. Pete has 3 marbles. How many marbles does Anne have?
Right, the one with the 62% success rate.
Yeah. A common incorrect answer, particularly among younger children, was 9. Now, the RGH analysis suggested this might be because the child lacked a combine schema and couldn't properly relate the parts to the whole. They were essentially seeing 2 separate sets, a set of 9 marbles for Pete and Anne, and a set of 3 marbles for Pete.
Okay, I can see how that interpretation wouldn't lead to the correct subtraction. You'd just focus on one of the numbers given.
Right. But the Leuven research dug deeper into why they were seeing it this way. By asking kids to retell the story and build it with actual objects, they discovered that many of these children were actually misinterpreting the word altogether.
Misinterpreting altogether.
They thought it meant that Pete and Anne each had 9 marbles.
Oh, so Pete has 9, Anne has 9.
Exactly. So their mental representation was Anne has 9, Pete has 9, and the question is about how many Anne has. Based on that understanding, the answer 9 makes perfect logical sense, even though it's mathematically incorrect for the original problem. It wasn't about not knowing they needed to subtract. It was about a fundamental misunderstanding of the initial situation.
That's a really powerful distinction. So it wasn't just a calculation error. They were solving a different problem in their minds entirely.
Exactly. And this focus on how children represent the problem also illuminated the incredible variety of problem-solving strategies they come up with on their own.
Ah, the strategies.
The Leuven team's longitudinal study really highlighted just how inventive these young mathematicians can be. Many of the strategies they observed weren't explicitly taught in the classroom. The children were constructing them themselves.
That's fascinating. What kind of unexpected strategies were they using?
Well, for some of the more challenging problem types, like that change 6 problem where you have to figure out the starting amount, Pete had some apples, he gave 5 to Anne, now Pete has 7.
Right, the tricky one.
Some children were actually using a trial and error approach. They would guess a starting number, subtract 5, and then see if they ended up with 7. If not, they'd adjust, try a different starting number until they found the one that worked.
That's quite a sophisticated problem-solving technique for a young child. Thinking algebraically, almost.
It is. The study also tracked how their strategies evolved over the course of the school year. They observed a clear progression from using concrete materials, directly modeling the problem with blocks or their fingers, to relying more on mental strategies based on memorized number facts.
Okay, that developmental shift makes sense.
Yeah. Interestingly, though, they didn't see as much verbal counting strategies as some other research had reported. The researchers suggested this might be related to the Flemish educational system's early emphasis on memorizing basic arithmetic facts.
That makes sense. Different educational approaches could definitely influence the types of strategies children tend to use. But did the semantic structure of the problem still have an influence even when they were using these more advanced mental strategies?
Absolutely. That was another key finding. The Leuven team's work confirmed and actually expanded on earlier findings by Carpenter and Moser, demonstrating that the semantic structure of the problem influences strategy choice even at the mental level. And for addition problems, not just subtraction, and those more hands-on material strategies.
How does that manifest itself with addition problems? What does that look like?
Okay, think about a change 1 problem. Pete had 3 apples. Anne gave Pete 5 more. Children overwhelmingly tend to start their mental calculation with the first number presented, so 3 plus 5.
Right, standard approach.
But if you give them a combine 1 problem, Pete has 3 apples, Anne has 7 apples. How many do they have altogether?
Cool.
They're much more likely to start their mental addition with the larger number 7 plus 3, even though both problems ultimately involve adding 3 and 5, or 3 and 7 in this case.
That's an interesting difference. So they're using the commutative property, but only for certain types of problems. Why?
The Leuven researchers propose that it comes down to the mental effort of reorganizing the quantities. In the dynamic change problem, the numbers have distinct roles. There's a starting amount and then a change that happens to it. It's cognitively harder to mentally flip them around and start with the larger one.
Okay.
However, in the static combine problem, both numbers represent separate sets that are just being joined together. There's less of a narrative sequence, so it's easier to just pick the larger quantity to start with for a more efficient calculation, like the counting on from larger strategy.
Okay, so the way the story is structured really influences not only their basic understanding, but even the nitty-gritty of how they approach the calculation itself.
Exactly.
Beyond the underlying semantic structure, did the Leuven team investigate any other aspects of the word problems that might affect how children solve them?
Yes, they explored a couple of other interesting task characteristics. One was the explicitness of the semantic structure in the way the problem was worded.
Explicitness, how clearly it's stated.
Precisely. Remember that Combine 2 problem about Pete and Anne's marbles? Pete and Anne have 9 marbles altogether. Pete has 3 marbles. How many marbles does Anne have?
Yeah, the tricky one.
They discovered that if they reworded it to make the part-whole relationship much clearer, for example, saying something like, Pete and Anne have 9 apples altogether, 3 of these apples belong to Pete, and the rest belong to Anne, even first and second graders were significantly more successful at finding the solution.
That rewording effect
Yeah.
makes a lot of intuitive sense. If you spell out the relationships more clearly, it's less likely that children will misinterpret the situation,
Yeah.
like that altogether issue.
Exactly. The researchers hypothesized that younger, less experienced children rely more on processing the problem in a more step-by-step, kind of bottom-up manner. They don't necessarily have a strong, automatic, top-down understanding of the underlying semantic relationships yet.
Right.
So that explicit wording essentially provides scaffolding and compensates for their less developed semantic schemas. This rewording effect is fascinating because it really highlights how much younger children depend on that step-by-step understanding rather than a broader grasp of the underlying situation, doesn't it?
It really does. It shows how critical language is.
Mm.
And what was the other task characteristic they looked at?
The other factor they examined was the order in which the given numbers were presented in the problem, and they focused again on those Combine 2 problems.
The order of the numbers, like which one comes first in the sentence.
Yeah. For instance, they compared problems that started with the smaller part. Pete has 3 apples, Pete and Anne have 9 apples altogether, versus those that started with the whole, Pete and Anne have 9 apples altogether, Pete has 3 apples.
And did that simple change in the order of the numbers influence how the children solved the problems?
It did indeed. They found that when the smaller number was presented first in the Combine 2 problems, children were more inclined to use indirect additive strategies, essentially thinking 3 plus what equals 9.
Adding up.
Exactly. However, when the larger total number was given first, they tended to use more direct subtractive strategies. 9 minus 3 equals what?
Wow.
This demonstrated that even within the same semantic problem type, just the way the information is presented can nudge children towards different, equally valid approaches to finding the solution.
So it's this intricate web of the underlying story, the clarity of the language used to tell it, and even the seemingly minor detail of the order of the numbers. It's clearly much more involved than just, looking for keywords like in all or left to decide whether to add or subtract.
Precisely. That keyword strategy is so often taught, but it's really superficial and often leads kids astray.
Right.
And all of these findings led the Leuven researchers to take a really critical look at how elementary arithmetic word problems were actually being taught in schools. They analyzed commonly used math programs for first and second graders and identified some significant patterns.
Okay, so they looked at the textbooks and materials. What were they observing in the materials that children were actually using in the classroom?
Several key trends emerged. First, word problems were often introduced after children had already been taught how to solve numerical equations, like 3 plus 5 equals 8.
Okay.
The implicit assumption seemed to be that word problems were simply an application of these pre-existing calculation skills rather than being a tool for developing conceptual understanding from the very beginning.
Right, which ignores their preschool abilities.
Exactly. As we've discussed, Children often come to school with a certain level of intuitive problem-solving abilities that just weren't being adequately utilized or built upon.
That does seem a bit counterintuitive, like learning the rules of grammar before you learn to speak.
Yeah, a bit like that. Second, there was a noticeable bias in the types of word problems being used in instruction. Most programs heavily favored those simpler change one, change two, and combine one problem types.
The easier ones.
The easier ones, yeah. While giving significantly less attention to the other, more challenging semantic structures like change 3 through 6 or combine 2, and often completely neglecting compare problems altogether.
So children weren't getting the opportunity to grapple with the full spectrum of problem types that could help them build a more robust understanding. They weren't getting the necessary desirable difficulties.
That's right, they weren't building that flexibility. And third, the instructional recommendations for using physical objects manipulatives to model the problems often didn't align with the strategies that children spontaneously invented and found successful on their own.
Hmm.
How so? It was as if the textbooks were suggesting one particular way to represent a problem with blocks, maybe focusing only on the action, while the children were naturally thinking about it in a different, sometimes more effective way, perhaps focusing on the sets involved.
That disconnect could definitely lead to confusion and potentially hinder their natural problem-solving abilities, kind of telling them their intuition is wrong.
Absolutely.
Yeah.
And finally, many of the programs they analyzed taught only one specific type of visual representation for word problems, often an arrow diagram showing jumps on a number line or something. While that kind of diagram can be quite useful for illustrating the dynamic changes in change problems, it's much less helpful, even confusing, for visualizing the static relationships in combine or compare problems, where things aren't changing over time.
Right. You need different tools for different jobs. So based on all of these insights into how children think and the limitations of current teaching practices, the Leuven team actually developed their own experimental teaching program.
They did indeed, and it was specifically designed to address the shortcomings they had identified. They flipped the script in a few key ways.
Like how?
They began by introducing word problems before formally teaching numerical sentences, really emphasizing that initial understanding of the problem situation first.
Situation first, symbols later. Makes sense.
Exactly. They made a conscious effort to use the full range of semantic problem types in their instruction, ensuring children were exposed to and wrestled with a variety of problem structures.
Okay, exposure to all 14 types, or at least more of them.
Yeah, much broader exposure. They encouraged children to use physical materials in ways that directly mirrored the underlying semantic structure of the problem. So, different ways of using blocks for combine versus change problems.
Matching the representation to the meaning.
Precisely. And crucially, they taught different types of diagrams that were better suited for representing the different categories of problems, arrow diagrams for change problems, part-whole diagrams, like number bonds, for combine problems, and matched bar diagrams for compare problems.
So, a toolkit of representations. That sounds like a much more targeted and thoughtful pedagogical approach. Did they see positive results from this experimental program?
The outcomes were very encouraging. Through pre-test, post-test comparisons with the control group using traditional methods, the children who participated in this experimental teaching program demonstrated significant improvements in their ability to both create accurate representations of elementary arithmetic word problems and, consequently, to solve them correctly.
That's fantastic. It really underscores the importance of understanding the cognitive processes involved, not just the procedures. And the Leuven team didn't stop there in their quest to understand how children think, did they? I understand they even incorporated eye tracking technology into their research later on.
Yes, that's another incredibly insightful layer to their work. They began to use eye movement registration as an additional method to gain even deeper insights into children's cognitive processes as they were reading and attempting to solve word problems.
Eye tracking. Wow.
Yeah. The fundamental idea behind this is that where someone looks and for how long they focus their gaze, their fixations can provide valuable, objective information about what they're paying attention to and how they're trying to make sense of the problem moment by moment.
So their eye movements are literally providing clues about their thought processes in real time, like a window into their attention.
Exactly. In one particular study, they compared second-grade students who were identified as having high and low math abilities as they worked on both simple and semantically complex word problems, like those tricky compare types. They tracked how long it took them to arrive at an answer and precisely where their eyes were focused throughout the process.
And what did their eye tracking data reveal? Did high and low performers look at the problems differently?
They found, first, that all children took significantly longer to respond to the semantically more complex problems. No surprise there. But crucially, this additional time was primarily spent looking at the words within the problem statement,
Ah,
suggesting they were working harder to comprehend the situation being described, not just staring blankly. But here's the really interesting part. After the very first reading of the problem, the students with higher math abilities spent more of their subsequent processing time focusing on the words.
rereading the text.
Right, seemingly ensuring they understood the scenario. While the students with lower math abilities tended to focus more quickly and more often on the numbers.
Jumping to the numbers.
Yeah, it hinted that the more successful problem solvers were prioritizing a deep understanding of the verbal description, whereas those who struggled might have been more inclined to jump directly to trying to manipulate the numbers without fully grasping the context first.
That's a really powerful insight into the different approaches they were taking right from the start, almost a difference in strategy revealed by their gaze.
It is. It provides objective evidence for that difference in focus understanding versus just calculating.
So as we bring this all together, what are the main takeaways from this decade of really in-depth research in Leuven? How does it refine or expand upon what we had learned from those earlier American studies by Greeno, Carpenter, and others?
Well, the Leuven research largely confirmed the critical role of semantic structure in problem difficulty, as initially highlighted by Riley, Greeno, and Heller. That basic framework held up.
Okay, so it built on that foundation.
Absolutely. However, it also contributed several crucial complementary findings. First, they identified numerous types of errors that the existing computer models couldn't fully account for. These errors often stemmed from children's incomplete understanding of the concepts and situations described in the problems, like the altogether example, or from their reliance on more superficial solution strategies, like just grabbing numbers.
Right, the models weren't capturing those conceptual gaps.
Exactly. Second, they also demonstrated that the influence of semantic structure on how children choose to solve problems is even more pervasive than previously thought. It affects addition problems and mental strategies too, not just subtraction and the use of concrete materials, which was the main focus earlier.
Okay, so broader impact.
Broader impact, yeah. And third, they really emphasize the complex interplay between the semantic structure of a problem and other factors, such as how clearly it is worded, that rewording effect, and even the simple order in which the numbers are presented.
So it paints a much richer and more nuanced picture than simply categorizing problem types and predicting difficulty based solely on the mathematical operation required. It's about the whole package.
Absolutely. The story, the language, the presentation, it all matters. The researchers also pointed towards important directions for future research. They suggested the need to investigate more complex, realistic problems involving multiple steps and different mathematical operations like multiplication and division to see how these semantic schemas develop and apply in more advanced contexts.
Moving beyond simple addition subtraction.
Right. They also strongly advocated for what they termed the broad spectrum principle, the importance of using a diverse array of research methods, combining things like interviews, observations, and testing with newer techniques like eye movement registration to gain a more comprehensive and reliable understanding of children's mathematical thinking.
Triangulating the data.
Exactly. And from a practical standpoint, their work provided, a compelling critique of traditional teaching methods and laid a strong foundation for the development of more effective instructional approaches in the classroom, like the experimental program they tested.
Okay, so for you, our listener today, what's the most important thing to keep in mind after this deep dive into the world of elementary math word problems? What's the big picture?
I think the key takeaway is that solving these seemingly simple math word problems is actually a remarkably complex cognitive process. It's deeply, deeply intertwined with how children understand the underlying situation being described, the story, and it goes far beyond just their ability to perform basic arithmetic calculations.
That certainly has significant implications not only for educators trying to teach math effectively, but also for parents and really for anyone who's interested in how children learn and process information in general, wouldn't you say?
Definitely. It underscores the critical need to foster a deep conceptual understanding right from the start. We need to help children build robust mental representations of problems, rather than solely focusing on the rote memorization of mathematical procedures or superficial keyword spotting.
So maybe a final thought for our listeners. Consider the next time you come across a problem that seems straightforward, maybe even when you face yourself, not just a child's math problem. how much of the challenge might lie not in the calculation itself, but in truly understanding the story it's trying to tell.
Hmm.
It really makes you think about how much our own problem solving relies on that fundamental ability to grasp the narrative behind the numbers, doesn't it?
It absolutely does. It's about sense making, first and foremost.